Thanks very much for the introduction. I'm Xiaoqi Chen from Princeton. I'm here to give a talk on behalf of my old friends Zizhong and Wang and other authors who, unfortunately, all of them cannot come here due to a travel ban from the United States and the coronavirus. So today I'll talk about C-Raft, a new consensus protocol. Before we dig into C-Raft, let's talk about distributed consensus protocols in general. The topic of this conference last session is consistency and reliability, so they must be very important. But why we need consensus protocol at all here? To improve reliability, applications usually store data into multiple copies on multiple servers. So in case when some of them crashed, there are other servers that can still serve the data. So here, we define two important parameters. There will be in total n servers, and we want to tolerate f of them crashing. In the example, we have 5 servers, and we want to tolerate 2 of them crashing. However, when data have multiple copies, we need to worry more about reliability. They may become inconsistent as well. One of the most important reasons that cause inconsistency is called network partition, where the servers are not crashing, but they cannot talk to each other. So maybe a user will show up and say, hey, I want to write x is 42, and this server says, yeah, I know x is 42. But another user will show up to the other server, x is 24, and maybe they say, yeah, I know x is 24. Later on, the users are gone, the partitions are recovered, but we don't really know what is x anymore. We need to provide a global consistency guarantee using a distributed consensus protocol. It is a well-established research area with a lot of different protocols. Basically, what we do is when we receive a write request, the server either say, hey, I'm not sure, I cannot complete the request, or it said, yes, I accept this request, the data is committed, I reach a consensus. So I'm very certain that the data was written. Even if I crash in the future, or other servers have crashed in the future, I can always read out the same data. So this is called global consensus. We also make an interesting observation here. If you want to tolerate F crashes, merely having 2 F servers are not enough. We cannot distinguish between the following 2 cases. Either I have F server in my cohort, and I cannot get in touch with the other F server, so they're all crashed, so I have to keep writing data. Or the network partitioned into 2 halves, and each of them having F servers, so I should just wait until the network recovers from partition, because each half of F server can keep writing. And it turns out we cannot distinguish between the 2 cases, so we need more than 2 F servers. One of the most widely used distributed consensus algorithm is called Raft. It is built upon the idea of majority voting, requiring n equal to 2f plus 1 servers to tolerate F crashes. By the way, this is also the optimal, or the minimum number of servers required. A server is elected as the leader when it has F plus 1 ballots from its followers, including 1 ballot from herself. Now, these F plus 1 servers, which is a strict majority, can reach consensus and commit data. Let me show a quick example. If we want to tolerate 3 crashes, we'll need 7 different servers. And maybe the first server becomes the leader because there are 4 green servers acting as the follower. So I get a majority to support me as the leader. Later on, if the data is written, the first 4 servers should save the data and say the data is committed. Later on, maybe the leader will crash and we'll need a new leader. In that case, no matter how we elect a new leader, it will also have F plus 1 followers, and the 2 group of followers will have at least 1 in common. As Raft requires a leader to have newer data than followers, the new leader actually will be this new green server. So the committed data is always preserved in the new leader election. Because we guarantee this overlap, we will not corrupt any already committed data. So we guarantee the global consensus. This crash resilience comes at a huge cost. So each server will store a copy of the data, and we want n times storage space. So for example, if the user sends us the data that's 1 gigabyte, so we have to send this copy to every healthy server we know of. So we need to store 4 or 5 gigabytes of data. We spend n times network traffic, and we also spend n times storage space. This is very wasteful. Naturally, we wonder, can we do better? We have a very powerful tool here, erasure coding, which is usually used for error recovery in wireless networks or in storage. Here, we use a particular code called Reed-Solomon code, just like many other papers mentioned today. We have 2 parameters here, k and m. The k-m Reed-Solomon code can split data into k plus m fragments, and each of them will have 1 over k inside. Some people call it k data shards and m parity shards, but they are actually symmetric. Let me show another example here. Say we use k equal to 3, and m equals to 2. So the data will be split into 2 plus 3 equals to 5 different fragments. Now, maybe each fragment will have size 1 over k, or 1 over 3 gigabytes. Now, maybe we're unfortunate, we will lost some of the fragments. We can use any k of the 5 fragments, which means any 3 out of the 5, to recover the original data. Given this tool, we wonder, can we use it to combine erasure coding with fault tolerance and get a new consensus protocol? We noticed that we already used 5 servers here, and to tolerate 2 crashes. And no matter what happened, maybe we'll have 3 servers as healthy. Can we just send 5 fragments, and then maybe 2 crashed? And we just use the remaining 3 to recover the original data. Well, the idea sounds simple, but because of the consistency requirements, we need to do more than this. There are prior works combining erasure coding and distributed consensus. RS-Paxos is a consensus protocol that has 2 parameters. QW is the size of write quorum, and QR is the size of read quorum. So basically, every write request have to write to QW different servers using different coded fragments. And a read request have to read from QR different servers. We further require QW and QR to follow this formula, which basically says for any write request and read request, we'll have k server overlapping. So for example, here we have 7 servers. QW is 4, QR is 6, and then they must have an overlap of k equal to 3. So for any data written into 4 servers, and any read request reaching 6 servers, we definitely see 3 different fragments, so we can recover the original data. Well, that's simple. But there's an interesting flaw of RS-Paxos here, that is liveness. If we only have 2 f+1 servers, we cannot tolerate f crashes. In fact, in this example, even if there are only 2 servers crashed, the system cannot be proceed. It will lose liveness. Why? Because we cannot read from 6 healthy servers anymore. So any read request has to fail. The Pendle paper presented on Tuesday upstairs at the NSDI conference presented some improvements over RS-Raft, among other things. Pendle tackled RS-Paxos latency issue, trying to reduce the number of reads it need by reducing the overlap between read and write quorum. So for example, here we can reduce the read quorum size to 4. They opportunistically read from fewer servers. When we send a write request, we wait until only 4 servers to finish the write. However, maybe we're lucky enough, actually there are 6 servers receiving the write request, so we have 6 fragments on 6 servers. Later on, the read requests come and only read from 4 servers. The parameters choice only allow 1 overlap, but maybe we're lucky enough to have 3 overlaps, so we still get the data. If that's not the case, at least we can use the overlap to see there's inconsistency, but we have to read from all servers in this case to try to recover. This algorithm is faster in the normal case, so it reduces the latency in actual operations. But the liveness issue persists. If 3 servers crashed, I can do nothing. Today we present CRAFT, a novel distributed consensus protocol that utilizes erasure coding. CRAFT is built upon the leader election protocol of the original Raft. Basically, you have 2f+1, we elect leaders in f+1, etc., strict majority. However, CRAFT differs from the original Raft that its leader does not send full copy of data to followers all the times. Instead, we will try to use Reed-Solomon code and send coded fragments. Here, the fragments are using Reed-Solomon code, and we choose parameter k and m such that k plus m equal to m, which means every server gets a different fragment. We also say k is smaller than f+1 because in the worst case, you have only f+1 servers, you want to recover the data. Data is considered committed when f plus k fragments are stored. Why? Let's use this example again. We have 7 servers to tolerate 3 crashes, and k is 3. So f plus k now is 6. If I write to 6 different servers, the data is definitely committed. Because for any future leader, it will have f+1 followers, we have k fragments overlap in common. So any future leader will be able to recover this data. This data is considered committed. There are a few challenges in our straightforward adaptation of erasure coding into Raft. And the first challenge here is the same as in RS-Paxos, which is liveness. Namely, sometimes there may be fewer than f plus k healthy servers. As we know, we have 2 f+1s, and f of them will crash. So in the worst case, we have only f+1 healthy servers. Our solution is to let CRAFT gracefully degrade to full replication when necessary. Namely, the leader will stop sending out fragments and start sending out full copy of data if he finds out there's fewer than f plus k healthy servers. Also, the leader does not know exactly how many healthy servers are there, because anyone can crash at any time, right? It will try to predict how many healthy servers are there using the recent heartbeat information, and try to use fragment replication, send out fragments if possible. But it will always fall back to send out full copy of data whenever necessary to guarantee that the system can always proceed, will not lose liveness, even if there are only F+1 healthy servers. Here we illustrate the process. In the normal case, all the servers are up. So we have 5 servers to tolerate 2 crashes, case 3. If someone user sends us a data, we can send to 5 different servers, including the leader. So now everyone can see the data. We have F plus K, so data is committed. Great. Later on, maybe some server will crash, and another write request will come. The leader knows that there are not enough servers to commit data using fragments. So now the leader will send a full copy of data to the other servers. So we have F+1 copies. Okay, great. We can also commit data in this case. The system does not lose liveness. There's a second challenge. When the leader crashed, we need to elect a new leader, and the new leader does not hold full copy of data. It only holds coded fragments. You need to be sure if these data are already committed, or I just got a fragment, I can't really recover the data. There are 2 cases. First, if the entry is already committed before, which means it already sent to F plus K's different servers, then any F+1 server will have K fragments. So new leader can always collect these K fragments by asking its F+1 followers, say, hey, if you have a fragment, please give it to me. Do you have it? Do you have it? Okay, there are K's people saying yes, they have it, so we can recover the data. Great. But then in the other case, maybe we don't have K fragments out of my followers. In that case, the data was not yet committed. So we may or may not have enough fragments by asking everyone. In that case, we may need to discard this data. We add a special leader prepare phase. When a new leader gets elected, we will try to recover these fragments. Either it can successfully recover the data because it's committed, or it failed recovery, and they will try to discard those data. To illustrate this, let's look at this slightly more complicated example. So the current leader will try to receive blocks and send fragment to everyone else. So data entry number 1 can now be committed by the leader because it's already saved in F plus K different servers, while the followers may or may not know it's being committed. As more data blocks come in, it gets replicated, maybe because network glitches, they did not get to that many servers. So say that block number 2 and 3 are less lucky. They did not reach F plus K servers, possibly due to network glitches, so they cannot be committed yet. In the normal case, leader will just try again, try harder and harder to make sure everyone commit that. But yeah, we're unlucky, so leader crash. We still have F+1 server, so system should be able to recover. So we'll try to elect a new leader. We follow normal Raft protocol to elect a new leader. According to some rules, we have this, the server with more entry or fresher entries will try to be the leader. So it will stand up to say, hey, can I be the leader? The other say, yeah, fine, I will support you. So I have F+1 supporters, I become the leader. In this case, it will first try to recover the blocks by collecting these fragments. For block number 1, it's already committed. So in the leader prepare phase, it definitely can be recovered. By reading this, I can make a new block. So I say, hey, block 1 get recovered. I can serve the read request for block 1. Block 2 is less lucky. It cannot be recovered. So we have to delete those. We notice here that we're deleting these fragments. It's different from the original Raft protocol where you never delete data. But we proved that it's okay, that we never violate the correctness as these fragments are not committed in the first place. So now I formally become the leader, I can serve new write requests. To recap, we proposed CRAFT, a consensus protocol that is, first of all, very, very efficient. By using erasure code, we save network and storage space. In fact, we use only 1/k fraction compared with the original version of Raft. CRAFT also guarantees liveness. First, it can always run as long as there are F+1 healthy servers. When there are fewer than F plus K healthy servers, we just gracefully degrade to send full copies to everyone. Second, after a leader crash, maybe there are a lot of fragments everywhere, but they cannot be recovered yet. We don't know how to do with them. We add a leader prepare phase here, trying to recover those fragments or delete those. The special leader prepare phase will try to collect the fragments and either recover or delete, and very soon move on to be the formal leader to accept new write requests. Finally, we guarantee the correctness of the distributed consensus protocol. The special leader prepare phase deleted some data, but we can show that the fragments being discarded are not committed in the first place. For more detail about safety and correctness of the algorithm, please refer to the paper. When we compare CRAFT with original Raft and RS-Paxos, we can see both CRAFT and RS-Paxos achieve the same savings in network and storage space because we're using the same Reed-Solomon code. However, RS-Paxos have a suboptimal liveness, as it cannot handle F crashes. Far before their F server crashed, the system lose liveness. It cannot proceed any new data. Now let's present some evaluation about CRAFT. We asked the following questions in the evaluation experiments. First, can CRAFT achieve higher throughput than vanilla Raft? The answer is definitely yes, because we have so many savings in network and storage that we expect it will be run faster. The second question is, can we achieve liveness upon F crashes? And the answer is also yes. Using the throughput curve, we can see the degrade process, but we can always run until there are F crashes. Finally, what about latency? It's more complicated in this question. For the write latency, we can actually get a reduced write latency. That's because for the write request, we actually send fewer data before we finish a write. For the read latency, it's intricate, because if you're a leader, you get a full copy of the data, you can always serve read requests just like before. So the only difference is upon the leader re-election. And the new leader takes some time to read the data back, so we have a slightly higher read latency when the new leader is re-elected. We'll talk more about this in the future slides. To evaluate CRAFT and compare against other consensus protocol, we implement the distributed key-value store application, or CRAFT KV. We let the system tolerate 2 or 3 crashes, which means we need 5 or 7 servers here. We use Reed-Solomon code with parameter k equal to 3, and we choose m equal to 2 or 4 to satisfy the requirement that k plus m is n, or every server will have a different fragment. The clients will send a read and write request to the key-value store, and we measure the performance, including throughput and latency, etc. All the clients run on a separate virtual machine, and all the server and clients run on AWS EC2 instances. We note that it's not straightforward to compare Paxos with Raft, so we implement RS-Raft to resemble RS-Paxos. It uses a very, very similar consensus procedure, have a read quorum size and write quorum size, etc. First, let's investigate the throughput and of the distributed key-value store using CRAFT. In these figures, the x-axis is the size of the value we're writing to the key-value store, and the y-axis the aggregated throughput of our systems. As we can see that CRAFT and RS-Raft, both of them enjoy network and storage saving, so they achieve higher throughput than the original version of Raft. And also the improvements are more significant when the value sizes are larger. We also know that on the left-hand side, we're using 5 servers. On the right-hand side, we're using 7 servers. CRAFT only needs 5 servers to tolerate 2 crashes, but RS-Paxos or RS-Raft requires 7 servers to tolerate 2 crashes. So we can also say that given the same amount of crash to recover, CRAFT actually get higher throughput than RS-Raft or RS-Paxos. Second, let us look at the liveness of CRAFT and RS-Raft. Here, we use n equal to 7 server to tolerate f equal to 3 crashes, and k again is 3. And the x-axis was the number of healthy servers. So on the left-hand side was 7 servers all up. On the right-hand side was the extreme case where 3 servers failed. There are only 4 servers healthy. Y-axis is again the throughput of the system. We first noticed that for the original version of Raft, when there are fewer servers healthy, we actually get slightly higher throughput. That's because you have to send to fewer servers. Raft will send to every server, but if there are some sort of crash, I don't have to send to them, so I get higher throughput. RS-Raft cannot work when there are more than 3 servers crashed. That is because the quorum size is at least 5, so we need at least 5 healthy servers. If there are only 4 servers, it cannot work. Now we look at CRAFT. The replicated coded fragment will only work when there are more than f plus k servers. F plus k here is 6. So if there are more than 6 healthy servers, we'll send the coded fragments out. But when there are fewer than 6 servers, we degrade by sending full copies out. So here, the performance degrades after we have only 5 or 4 servers, but the system still works, so we still have liveness. Now we discuss the read latency in more detail. We know that the leader server holds full copy of the data. Therefore, you can serve read requests right away. However, if the leader crashes and we elect a new leader, the new leader must collect the fragments before serving the read request. So the first read immediately after leader re-election will incur extra latency. As we plot here, Craf used about 1.6 to 1.8 times latency compared with the original version of Raft due to this collecting fragment process. However, this is only for the first read. If the same value was read multiple times, same key was read for multiple times, then on average, we don't have that much impact. Only the first read would need to collect the fragments, and the future reads are just like the original Raft. It's the same performance. In summary, today we present Craft, a consensus protocol utilizing erasure coding to lower the network and storage overhead. Craft ensures correctness and, more importantly, liveness. It guarantees the system can still run with F server crash out of the total of 2F plus 1. Thanks to the lower network and storage overhead, Craft achieved significantly higher throughput compared with the original Raft consensus protocol. I'll conclude here. I'm happy to take any question and try my best to answer. You can also more than welcome to talk to me offline or send email to the first authors. Thank you very much.
Juan, AWS. Great work. One question that I have is in Raft, it's extremely simple for me to understand how the log catches up when you're electing a new leader, right? Just, but here I don't see how that is happening because you have all this fragments spread. So can you describe a little bit about that part?
So the question is, how can we catch up? So if a follower was very far behind the original leader, in the original Raft, the follower can simply ask the leader for some snapshots to quickly catch up. So in our protocol, it's also possible to do this full copy snapshot catch up from the leader, although that's not the most efficient way. It's also possible for the follower to try to ask k different peers for k different fragments. But we noticed that the end goal was not to get a full data for every follower. We actually want to store the fragments, not a full fragment. Want to store the fragment, not full copy. So it's better that once I get a full copy and catch up, I coordinate with the leader and make sure that if the data is committed, I will reduce my full copy back into the smaller fragments to save storage space. So basically it happens as follows. If I'm far behind, I will stand up, I will go to leader, I got all the full copies, and later on I check whether it's committed. If it's committed, I change my full copy again into the smaller fragments to save it. I hope I answered your question.
Hey, Nick at Cumulo. As someone who works on a Paxos-based distributed file system that uses a lot of this and has in it currently a restriction on the liveliness that you talked about, it seems like this could be applied to a Paxos-based system generally, having each server node sends the full copy to other nodes when some subset is down. Am I missing something?
I think your understanding is correct. Yes, the same technique can also be applied to Paxos. It's just a different style of Paxos and Raft. The technique we presented here was more focused on graceful degradation and also the liveness part. Yeah.
Cool. Cool work. Thanks.
Thanks.
Hi, this is Shao from ByteDance. I have a question about the performance evaluation. Can you turn back a few slides?
Sure. This one?
To the, maybe the next one, yes.
This one?
Well, actually, can you go back? Can you go back? Yes, I think it's this one. Yeah, this one. So I think you mentioned that, like for Craft, after you have less than 6 replica healthy servers, you're going to switch to send full copies, right? Yes. Now, why in this case you're still significantly faster than the vanilla Raft? Because now you're sending full copies, so I presume they're actually equivalent. Okay, good question. Actually, we have a backup slide for this. So basically, we noticed that the end goal of the system is to save fragments. So if there are fewer than 6 servers, we will send to F+1 full copies and more fragments. So basically here we will say 4 full copies and 1 fragment. The reason why we're sending this fragment is because if at the end of the day, there are more servers becoming healthy, they catch up, then this server can be committed differently using F+K fragments. So the difference here when there are 5 servers, essentially the Raft is sending 5 full copies and we are sending 4 full copies plus 1 fragments. But in case you just have 5 healthy servers, basically that fragment is not getting used. Right? Yes, yes. So currently it's not getting used, but as we discussed earlier with the other question, if there are more servers becoming healthy, they will catch up.
If we show that now we have 6 servers, as 4 full copy plus 2 fragments, then the 4 full copy can get degraded back into fragments, so we have 6 fragments. So we can later on change the full copy back to fragments to save storage.
Sure, but here, the numbers you show, are they operating under the condition that you always only have 5 servers, or do you have servers coming back to utilize that fragments?
Yeah.
If not, I'm kind of failing to understand, if you only have consistently having 5 servers, how does that fragments are able to help you?
Yes, so here we are assuming that we have 7 servers, so it tolerates 3 crashes, and hopefully more servers will get back. If we only always have 5 servers, we need to operate differently. So 5 servers can only tolerate 2 crashes, and 7 servers tolerate 3 crashes. Hopefully, maybe more will go back. So 5 will become 6 or 7 later in the setup.
Right, but yeah, that's later, but still you're showing a significantly higher throughput here.
Let's discuss offline.
Okay. Okay.
Yeah, sorry, I have the same question, but you didn't explain why in 4 servers, those 2 bars should be the same height. That your fragment argument doesn't help there, I don't think. But
yeah, so given that if it's always 4, it's the same as 4 server, we should degrade it to RAF already, but why we're still faster a little bit? Oh, that's because in experiments, even before sending out, there are some preparation specific to different protocols. So for RAF, both RAF and CRAF, they have their own prepared phase before they actually send out. So in different implementation, there are some time consuming before we actually start sending the data. So even if we degrade, we send a copy of data, it's slightly different from the original RAF implementation where you just send it out. So there are just some artifacts in implementation. Thanks very much for the question.
Okay, great. Let's thank our speaker again.
Thank you.